Hello, Professor Lee, Andrew, Maisha. We're Group 26. Here's the outline of our presentation. According to the U.S. Environmental Protection Agency, transportation contributes to 30% of the greenhouse gas emission in the U.S. With the looming environmental issues, vehicles powered by PEM fuel cells are considered as green solutions since they produce near zero emission. In a PEM fuel cell stack, bipolar plates account for 20% of the PEM fuel cell stack cost and 80% of its weight. As one of the most important components in the PEM fuel cells, bipolar plates are used to serve functions such as electrical connections and mechanical support between the cells. Considering the operation conditions of the PEM fuel cells, bipolar plates should possess high electrical conductivity and a good corrosion resistance. Currently, carbon-based polymer composite and metallic bipolar plates are commonly used in the PEM fuel cells, especially for automotive applications. Although composite bipolar plates feature high corrosion resistance and low weight, their low conductivity affects their performance. Metallic materials such as stainless steel possesses electrical conductivity and high manufacturability. However, their poor corrosion resistivity can lead to metal dissolution that reduce the cell performance. First, we will take a close look at the composite bipolar plates. As mentioned above, polymer composite bipolar plates generally have low electrical conductivity, which handicaps the fuel cell's performance. The U.S. Department of Energy set the target for the electrical conductivity for bipolar plates to be higher than 100 siems per centimeter. To achieve the DOE target, the most researched method is to incorporate conductive fillers such as carbon nanotube into the composite. And the conductivity of the bipolar plates using the carbon nanotube fillers typically fall into the range between 80 and 174 siems per centimeter. Typically, injection molding is considered as a cost-effective way to produce composite materials due to its high throughput rate. However, injection molding introduces high shear forces, which alters the orientation and dispersion of the conductor filler, reducing the electrical conductivity of the composite. To avoid this unwanted feature, most of the composite bipolar plates are manufactured by compression molding at the expense of the low production rate. The typical cycle time for compression molding ranges from 60 to 360 seconds. That is more than 10 times longer than the compression molding. Therefore, it is necessary to find an alternative material and simultaneously meet two design objectives. First one is to achieve comparative composite electrical conductivity with the composite using carbon nanotube fillers, and the second one is to enable processing techniques with shorter cycle times than compression molding. Researchers in the aerospace industry have identified a carbon nanotube-based material, bucky paper, to be a good potential solution. Since its structure can withstand the shear force and remain well orientated after curing, it appears to have good potential to be used in composite bipolar plate manufacturing. To make bipolar plate composite from bucky paper, vacuum-assisted resin transfer molding, VARTing, can also be used. Generally, the process takes 4 steps. First, a bucky paper proform is placed in the mold. And after sealing the mold, resin is injected into the mold while vacuum is pulled to allow infiltration of the resin. Lastly, the infiltrated bucky paper is cured at an elevated temperature. In order to predict the electrical conductivity of the composite bipolar plate made with bucky paper without conducting an experiment, a numerical model is needed, which is showed on the slide. This plot illustrates the predicted correlation between the volume fraction of the additional bucky paper above percolation threshold and the conductivity of the composite in logarithm scale. The optimum filler content is reached at 2.4% of volume of bucky paper. That is corresponding to an electrical conductivity of around 81 siems per centimeter. The result shows a promise of using bucky paper, as the predicted electrical conductivity is very close to the DOE target. In addition, the use of bucky paper in composite bipolar plates enable higher throughput. Specifically, using VARTing methods mentioned above shortens the cycle time to below 50 seconds, as opposed to 60 to 360 seconds using the state-of-the-art compression molding.
I will be introducing the metal bipolar plates in PEM fuel cells. To improve the corrosion resistance and the electrical conductivity of metal bipolar plates, current solutions involve the application of coatings to metal surface through processing methods such as physical and chemical vapor deposition. but this method can lead to undesirable increase in surface contact resistance and overall efficiency reduction. For example, the contact resistance of PVD-coated stainless steel is measured to be around 160 milliohms square centimeters, which is 8 times above the DOE target of 20. Also, the dissolution of metallic elements from bipolar plates can contaminate the fuel cell membrane, leading to accelerated efficiency reduction. Deep coating, a fast and effective sol-gel coating method, will be used to replace the current coating on bipolar plates. Metallic bipolar plates are dipped into a fluid for gelation, air-dried, and then heated for densification. Sol-gel coating are proven with experiments on their enhanced corrosion resistance for metals, as well as their conductivity. Organic and inorganic hybrid sol-gel coating is a good candidate for metal corrosion prevention. Organic sols in the hybrid coating can repel water, form dense thick films, and reduce coating porosity. In comparison, inorganic sols can form chemical bonds between metal and hybrid coating, enhancing their interfacial adhesion. The ratio of inorganic and organic components of the hybrid coating can be optimized to achieve different effects for different applications. The interfacial adhesion strength is influenced by the compressive residual stress at the interface between the coating and the metal. As indicated in the equation, coating thickness and residual stress are inversely related. As coating thickness increases, surface residual stress decreases, which leads to lower adhesion strength. Even though the increase in coating thickness leads to a decrease in adhesion, corrosion resistivity can still increase. As a result, there is a trade-off between adhesion and corrosion resistivity. The proposed hybrid coating material mainly consists of PMMA and TEOS. The composition of TEOS in the hybrid materials varied from 0% to 25% to find the most optimized result. The protection efficiency is calculated by the equation based on the corrosion current density of the substrate with different coating compositions. The results show a significant change in protection efficiency and corrosion current density as the content of TEOS increases. More TEOS leads to lower corrosion current density and higher protection efficiency. The DOE target for corrosion current density is 1 microamps per square centimeters. Thus, the target can be achieved with compositions of 75% of PMMA and 25% of TEOS. The results proves the potential success of achieving the DOE target for the proposed coating technique and the material with properly selected composition.
For the metallic bipolar plates, our quantitative analysis involves the corrosion rate calculations with this equation from the book of corrosion engineering. There are two important inputs to this equation, which are related to the physical and chemical properties of the corroding species. The equivalent weight of the corroding species is given by the atomic mass divided by the valence that contribute to the combining power in the reactions. For stainless steel, this corroding species is chromium. For PMMA silica hybrid coating, the corroding species is silicon. So they have different equivalent weights and densities. So when we plot the corrosion current density together with the corrosion rate for our various samples, we realize that there's an increased material loss with PMMA silica-only coating at almost 15 mils per year. But this immediately reduces to 4 mils per year with 5% addition of tetraethyl orthosilicate, or TEOS. This trend is not very obvious in the corrosion current density values, so there appear to be an advantage to use the corrosion rate calculation when predicting the protection provided by these coatings. In conclusion, we have discussed two types of bipolar plates used in PEM fuel cells for automotive applications. Both of them have a set of positive attributes as well as challenges. To overcome the fiber orientation issues with the carbon nanotubes, we are proposing to use bucky paper for the composite bipolar plates. It has the potential to yield desirable conductivity and can enable more flexible processing technologies for reduced cycle time. For metallic bipolar plates, An inorganic hybrid coating is investigated as a candidate with sol-gel technique. This ensures lower corrosion on the plates and improves the efficiency of the overall PEM fuel cell system. In terms of future perspectives, both proposed solutions require experimental validations as the performance of the materials vary with the complex interplay between manufacturing technologies and the materials. This is the end of our presentation. Thank you very much for your attention.